Well, that way you can't.
Okay, let's get started. Who knows how long the power is going to last? So, yeah, so exam 3 on Thursday, right? You get an 8.5 by 11. This test is going to be a little different, right? It'll be a lot of the concepts, but it'll be kind of like quickie answers type stuff. You know what I mean? Like you have a question, it might be 5, 10, 12 parts to each problem because it's like, what's the synchronous speed? How many poles? What's the efficiency? That type of stuff based on some information. And so the reason why that is because a lot of this is just based on previous stuff we've done. It's just applying it to induction motors, right? And the whole thing about an induction motor is it does not operate at synchronous speed, meaning its mechanical speed is not the same as synchronous speed unless it's being driven by an external prime mover. Now, that doesn't mean synchronous speed doesn't exist. It still exists. So remember, there are two magnetic fields, one on the rotor, one on the stator. The stator magnetic field, usually that's where the current comes in to drive an induction motor. That's going to be 60 hertz, and that's going to create a magnetic field that rotates at synchronous speed. And we can find that by doing our right-hand rule, taking our fingers and pointing. And so we've done that extensively. That's the magnetic field that we're talking about on the stator. On the rotor, because you have windings, three-phase windings on the rotor, and they're short-circuited, you can have current flow through there. And that current flow does exist because you have magnetic fields that are changing. The magnetic fields that are changing is you have rotations at synchronous speed, plus you have actual physical rotation of the shaft, essentially, or the rotor. And the rotor can operate at synchronous speed because if those two are operating at synchronous speed, there'd be no changing magnetic field, right? You have a hunk of wire spinning at the same speed as the synchronous speed, so there's no changing magnetic field. So there always has to be a delta. The AC of the three-phase windings are going to create an AC voltage and current that is going to flow on that rotor circuit, and that's going to make up the difference between the mechanical speed of rotation and the synchronous speed. All right. So if you think about things from the perspective of living on the rotor, you see a magnetic field that is 1800 RPMs, but the rotor is spinning slower than that. So you're spinning slower, but the magnetic field that is created from the actual AC currents on your machine, those are spinning along at the same speed. So if you could imagine, you see a stator magnetic field and then a rotor magnetic field, and those are spinning at the same speed. So you have to think about things in terms of where your reference is. Am I stationary? Meaning, am I standing right next to the stator and looking at it not moving? Am I on the rotor, which is I'm spinning along and I see something that's spinning along slightly faster than I am? Or am I actually spinning at synchronous speed and then looking at things that are spinning at a slower rate than I would be? Again, that's only the case for an induction motor. So when we do that, it helps us understand like how this actual machine operates very efficiently, very effectively, and you can have variable speed characteristics. As a matter of fact, you have to have variable speed characteristics because it's depending on the load. The slower the motor is, the more current you're going to do. It's going to try to spin you up until you exceed the limits of the machine. Okay, so make sure you understand the concept of slip, because every induction motor has to operate on the concept of slip. And again, slip can be between 0 and 1, which means no slip, which means it's running at synchronous speed, or 1, which means it's fully slipped. It means it's not rotating at all. So that's the difference between no slip and locked rotor or blocked rotor conditions. And we use the term locked rotor or blocked rotor conditions a lot because it allowed us to get to our equivalent circuit. So once we have the concept of slip, we know that sort of that relative speed between what the mechanical speed is and the synchronous speed. Then that slip is going to give us what the AC electrical system needs to produce to pick up the difference. And as a result, we can use that to calculate the electrical frequency. So on a three-phase induction machine, on the rotor circuit, you actually have a variable three-phase variable frequency device. And as I mentioned in this class, it wasn't that long ago, they had things called rotary converters that if you could access the rotor circuit, you could have a three-phase set of AC windings at whatever frequency within reason that you wanted. Okay, so pretty important to look at that. And then you can see some examples. If you go back into the examples, you can take a look on, seeing some examples there. And because of that variable speed capability, we really have to look at the machine in terms of its speed of operation. So we developed torque versus speed characteristics. And torque was the dependent variable. Speed was the independent variable. And that's a little bit misleading because it really isn't an independent variable, right? And the reason why is because you actually have to have load on it. The more load you have or the less load you have varies the speed. But the load is a mechanical system, and we're not going to really super focus on that part. We're looking at how does that speed of operation affect what output torque you can produce. So our speed varies from 0 to synchronous speed, and it's going to produce a torque. We want our machines to operate as close to synchronous speed as possible because that's where we achieve higher levels of efficiency. So if you look at full load operation, it tends to be almost at synchronous speed, really, really close to synchronous speed. So values of slip of 3% or less are very common when you're talking about a real world application. And just because the induction motor is rated to produce, let's say it's 100 horsepower, 200 horsepower, that doesn't mean it has to operate at 200 horsepower. So if the mechanical load is less than the 200 horsepower, that motor is going to speed up until it matches whatever the mechanical load demands from it. So just because it is capable of providing 200 horsepower doesn't mean it's actually providing 200 horsepower. Again, it's all based on the load. The mechanical load is what's going to dictate what the speed of operation is. Now, you can change that a little bit by having a variable frequency drive, but then what you're doing is you're monkeying with synchronous speed. And so you're kind of changing the characteristics. We didn't talk too much about that, but hopefully you can start to see, hey, if I change the speed, the mechanical load is going to have a preferred speed of operation so that it's not running too fast or too slow. And then I can go ahead and adjust the efficiency of the induction motor by running it higher and higher levels of slip relative to that new synchronous speed. Here's our equivalent circuit, and I will add or note that this R2 over S is the full representation of the rotor circuit. Again, everything has been reflected to the stationary side, right? So we don't look at the block rotor conditions because those are really hard to get. But we reflected everything over to this equivalent circuit. The equivalent circuit looks awfully similar to a transformer, except again, we're short-circuited on the rotor circuit. But that R2 over S is the combination of R2 and, R2 times 1 minus S over S. R2 is the rotor resistance. And R2 times 1 minus S over S is equivalent to the torque output. Okay. So again, that's another big change because in most cases, we haven't figured out a way to accurately predict what's happening in terms of, hey, we have a torque on this machine. Well, that's power. And we can add a resistor in there, but this is the first time that we've actually done it. And it's so important to do in induction motors because that's their whole purpose in life, right? Is to provide a mechanical output torque. So you can see that R2 times 1 minus S over S, the higher the value of slip, the closer it gets to 1, right? The more and more it approaches that ratio of R2, or I should say 0, right? So at no speed, right, when we're fully slipped, block rotor conditions, no output power. Really, there's no torque, correct? I mean, that's not 100% true, but there's really no torque. And there's no torque because power equals torque times omega. If omega equals 0, power has to equal 0, right? So you can still have torque, right? If you think about it, if you ever try to take a set of lug nuts off your car and you're sitting there straining away, nothing's moving, you're putting a lot of torque on those nuts, right, to try to get them off, but they don't pop. It's only when you start spinning that they actually are doing some power. Over here, you can see that same characteristic. If we move all the way up to 0 slip, which we can never achieve, we see that R2 times 1 minus S over 0 approaches an infinitely large value. And so we can see that we get no current flow under those conditions. But under really small conditions, R2 times 1 minus S over S is going to limit the amount of rotor current, which means it's going to limit the amount of rotor losses, right? Because R2 is the rotor losses, I squared times R2 is just heat. So the lower you can get that current, the less you have for losses and the more efficient the motor is. And it doesn't really affect the power output because you can see R2 times 1 minus S over S. If R2 is sky high, I squared times R is still going to be a pretty high number, right? So I don't need a lot of current to drive a lot of power, particularly if that value of resistance is really, really high. So that's really, really helpful sometimes to break the terms up. I showed it as R2 over S, and that's because if you remember in class, I showed you two ways to analyze these systems. Number one was using Thevenin equivalents and series parallel combinations and doing that to your heart's content. I don't know if that's the best way to do it, but it is one of the ways to do it. I prefer doing it with just plain old circuit analysis. And so what I've shown you, instead of rewriting it over here with the full derivation, I just showed you this is the set of loop equations to solve for the stator current and the rotor current. And this is just memorization, right? You put the values in, you're good to go. You can see that I've got V phase and 0 because there is no voltage source on the rotor circuit. There's no developed voltage there. And that's the value. If you are going to do it this way, that's perfectly fine. Just make sure you show your work as to where you got the equation from, right? So just show, you don't actually have to put an R1 and R2 and all those numbers. You can just show the value and then you say, I got IS and IR from here. Now your calculators should be able to do this, but I know MATLAB can, right? That's what we did in class when we developed our own torque versus speed characteristics. This directly gives you, come on, scroll up. That approach gives you IS and IR. So if you're calculating losses in machine, it's great because I know what the stator current is, I know what the rotor current is, and I've got the model. So I can include or calculate stator copper losses, magnitude I1 squared, right? Not I1 squared, magnitude I1 squared. I can do core losses if there's a way of calculating it. Usually there isn't, so we usually ignore it. I can calculate the rotor copper loss here, and I can calculate the induced torque, not the output power, or not the induced power, not the output power, but the induced power. And the reason why I can do that is because I know what I squared I2 or IR squared times this R2 times 1 minus S over S is equal to. Now that doesn't include any of the friction and windage losses because those are all torques. And I'm not going to include, you know, all those additional losses and additional circuits. We'll let our mechanical engineering friends worry about, you know, what bearings to specify and all that good stuff. But this one I find to be really super duper helpful because if I can plot a bunch of these currents, or not currents, but if I can plot a bunch of powers or torques versus speed, I can derive my own torque versus speed characteristics. And looking at that torque versus speed characteristic, I can get pull-out torque, I can get startup torque, I can get all those parameters off that one curve. Read.
Are we gonna have to do that on the exam?
You'll have to calculate the torques, yes, but you won't have to do a plot showing, you know, all the different points and doing it that way.
Is there a way to calculate the maximum torque?
Yeah.
Easily?
Yes. Well, relatively easily.
Is that equation on this? I believe I was looking through the, oh, okay. That's the, oh, okay, right there. Okay.
That's the way that if you want to do it with approximations.
So that's just the max torque,
Which is pull-out torque. Yep.
And then for starting torque, is that that's the,
How would you solve for starting torque?
I guess you just plug in a negative 0. Is that not, that wouldn't work?
That's omega sub S, that's synchronous speed. I would plug in S equal to 1.
Oh, okay.
Right? Starting torque is when S equals 1.
Okay.
I wouldn't plug in actual omega sub M because it doesn't call for it here, right? It calls for omega sub S. So nowhere in here is that dependent on the Megas event. But yeah, you can calculate it from here.
Okay.
Or, like we did in class, you can build your own torque. It's a speed characteristic. Totally up to you. Your choice. Just make sure, you show how you got that. If you went to MATLAB and you just said, oh, I got this, you need to make sure you show how you got those parameters and that you entered them in correctly. Okay. All right, power flow. And the nice thing about power flow is this is how you can calculate losses and efficiency in an induction motor. Since we're only talking about induction motors, we're always going to have input power be electrical. And this is a three-phase machine. We only did induction motors that were three-phase. We never did any single-phase or smaller than three-phase machines. It just doesn't make a lot of sense because they don't really exist all that often. Or if they do, you're not going to analyze them, right? You're going to buy a refrigerator and throw it away. You're not going to sit there and calculate what the load current is. You're just going to say, hey, this plugs into a 15 amp receptacle. It's good to go. But we have our PN, and if you look at our equivalent circuit, we have stator copper losses, then rotor copper losses. And at that point, all the losses that are because of the stationary elements are gone. Now everything has to transfer across the air gap into the rotor circuit. So that energy that transfers is called our air gap power. Now we have some rotor copper losses, and that's the only resistor that we have that dissipates power. There is power being dissipated, but at that point, that is power that is available to the shaft. So that power is converted from electrical to mechanical. Now we have to take off all mechanical stuff. So that has nothing to do with electrical. It's just the fact that we live in the real world and we have friction and windage and any uncharacterized losses stray. And then our output power is just proportional to your load torque times not synchronous speed, but mechanical speed. Okay? Because the speed of operation is not synchronous speed, it's mechanical speed. And that's where you calculate power. Here's a bunch of equations. You can take a look at them. They're pretty basic. But the whole reason why we have all these equations in here is to show you for every unit of power we have that crosses the air gap, 1 minus S unit of power is converted power, so converted to mechanical. The S percentage or the S ratio, if you will, of that power that gets converted is lost to heat. So hopefully what you can see, the lower the slip, closer to zero, the more efficient the motor operates, right? Because more power gets converted than is wasted as heat. But you're welcome, to write these equations down, but hopefully these are pretty self-explanatory. Stator copper losses, I squared R. Rotor copper losses, when we combine the two resistors that we just showed, that's all the air gap power. That's all the power that goes to the air gap. Then we have rotor copper losses, and then the air gap power. Again, now we break that resistor, that R2 apart, and then we get the converted power. So that's why I show it one way with the easiest representation, but then we marked up the figure and we show how we can break that resistor up into two separate resistors, because if you can interpret how that is laid out, it really helps you with an understanding of how the system or circuit works. And then our output power, again, just looking at the diagram, friction and windage and stray, if you subtract that from converted, you get your output power. Nothing summary there. Last thing is if you want to calculate, well, actually what we talked about with Reed is if you want to calculate max power, you're only looking at conveying max power, which means you have to have your Thevenin equivalent impedance. So your stator equivalent has to be, your magnitude has to look like the rotor equivalent. And so you just make these assessments here, the assumptions here. Again, we're not going to derive it because there was a bunch of work to derive it. At this point, hopefully you know how to use it. And then you can go ahead there and substitute it, get an equation for T induced, which is just based on those Thevenin equivalents. And then you can calculate for your slip at max pull-out torque, so what the actual slip speed is. You can also calculate what your pull-out torque is, going back to what Reed said. Or you can just draw torque versus speed characteristics, right? Either one. But you have to start not doing while loops or for loops and You have to not be an advanced MATLAB code person. You just have to understand like, hey, I have to iterate through and keep track of things. So I showed it to you two ways, take your pick. And then we saw how we can monkey with R2, right? We can increase R2. And we saw how we got smoother and smoother, meaning our starting torque got to be a higher and higher value as we went from ANEMA A all the way to ANEMA D. Then we saw how we got really high starting torque, but then our slip was pretty high when we had our full load torque or our steady state value. And so a Class D motor is not going to be as efficient as a Class A or B or C. Class B is a nice compromise between Class A, which is highly efficient, but has crap starting torque. And Class B has pretty good starting torque, good pullout torque, and then operates relatively efficiently. So that's why most of the motors are NEMA Design B, except again, you have an application where you're starting a really hard, heavy load, and you need a lot of torque to be able to do that. Okay. You're going to pay a price and not a very efficient motor, but you can start your load, which is probably the most important part. So I summarized the loop equation there. Again, you can take your pick and you can go from there. And then lock rotor tests. So just like with transformers, when we did open circuit and short circuit tests, define equivalent circuit parameters, we're going to do the same thing for induction motors. So induction motors, because it's rotating, right? We can't necessarily do, an open circuit or short circuit test because what we're stuck with is the rotor is already short circuited. So we can't really open circuit that. That's not possible. So we do the equivalent from a mechanical perspective. We do blocked rotor, right? Which is like the maximum that we can have, which is essentially the short circuit conditions. And then we do the no load or as lightly loaded or as open circuited as possible. So that's the corollary between the two worlds. So a DC test is also needed to get that value of R1, right? We have to tease out our value of R1, but then block rotor and block rotor and no load speed tests will allow you to calculate those specific values. If you remember under block rotor conditions, right? Our value of S, well, let's go all the way up over here. Our value of S is equal to 1. So now we can measure the PN and voltage and current, and we can go ahead and make some assumptions about throwing that in the trash. And we have enough information to go ahead and do that. And then we go into the no load test. Essentially, all we have, this circuit is out, and then everything goes through here. So your no load tests give you those two parameters, and then your block rotor kind of give you the rest all in series. And so that's why you don't normally you're going to get the no load tests. Sorry, yeah, the no load test and get your R1 and X1, and then you can tease that, and then you can start to get information about X2 and R2. But you can't tease out enough. You need to have some way of getting R1. So you really only get R1 with the DC test. You get X1 with the no load test, and then you get X2 and R2. And I'll put this under a combination. You need no load and lock rotor. And this test, you need no load, lock rotor, and the DC. So you need those three tests to be able to calculate what R2 is. And even with that, we still don't have enough information. So we have to tease out the different ratios of what is our value of X, because we don't have a way of teasing out X1 and X2. And so that's why we have our lock rotor tests and we have ratios, and it's based on the type of induction motor it is. If it's NEMA Design B, so our X1 is going to be about 0.4 of the lock rotor, and our X2 is going to be about 0.6. Okay. And as we saw in lab, really hard to get those curves, right? Really hard to get those parameters. We can certainly get our tests. We can run our tests. We can do block rotor and we can do no load tests, and we can get a lot of those parameters. We can calculate it, but in lab, if you remember, we couldn't run under blocked or lock rotor conditions. You can do that, but you physically have to put like a pipe wrench on the shaft and lock it in position. I tried to do it one year, but we ended up scouring a shaft because usually you just take a pipe wrench and you lock it into position and it digs in and it leaves gouges on your lock rotor. I think what they do in industry is they have some kind of a wrap or something that they lock it into place, or they just do the same constant. They just bolt something to it and they leave it in position and hopefully it doesn't spin, but they might have destroyed that motor. So maybe they have a sample one that they're willing to destroy. The other hard part too about lock rotors, you can only run that test for like 10 seconds and then you got to shut it down because the motor is really working hard. If you remember when we were doing it in lab, for the physical lab, it was working. You could hear it grinding away, but we don't worry about that. And then if you start a motor, you've got to look at the KVA code. If the KVA code, which tells you the number of KVA per nameplate horsepower, tells you how many KVA you need to start, you can calculate the current. So if your system can handle a large inrush, start it across the line. That's the cheapest, best way to do it. If it can't, then you're going to have to do with reduced voltage starters, which are those auto transformers we talked about, or you have to use a variable frequency drive. I would not buy a variable frequency drive just to reduce start the motor. I would buy an auto transformer one as long as I could. Because buying a variable frequency drive is going to be a pretty expensive endeavor. And it's going to have maintenance and yada, yada, yada. Plus you got to set up and configure it. So probably not the best investment of money and time to do that. But how do you know that a system can't handle starting a motor? Voltage drops, right? If I'm pulling 10,000 amps and I got a transformer and wire that has impedances associated with it, if I pull so much current, those impedances cause me to get greater than a 10% voltage drop across the motor, it's possible that the motor won't start. And part of the reason that is there's something that starts a motor is called a motor contactor. And essentially, these are the three AC lines that feed the motor. Normally, we run two of those lines, through a control power transformer, and that feeds a bunch of stuff that will help us start the motor. If the voltage drops to below 90%, you get a dropout. Your voltage is not sufficient to maintain the connection, the devices in there. And so it stops and doesn't do it. Also, there's some requirements too about National Electric Code. I'm not sure how much the National Electric Code applies to motor starting, but there's a rule, 3 to 5%. But if you're starting a motor, I think you can go up to 10%. And after that, you have to change it out. So one of the ways to do it is you can buy bigger wire, right? You can reduce the impedance. Problem is that's very expensive. That means more copper, which ain't cheap. You can buy a transformer that has a lower impedance. Is that okay? Maybe. The problem is whenever you have a fault on the low side of that transformer, you're going to get boatloads more fault current, which could potentially mean your system gets more damage. Or you can just say, you know what, I'm just going to buy a low voltage starter or a starter that has low voltage capability, start the motor, and then once it gets close to running speed, switch on to that speed. As long as I'm allowed to run for a period of time and I won't damage the mechanical system, that's by far the preferred way. And you can go to any, you can go to GE, you can go to Siemens, you can go to ABB and look at their motor control centers, and they have all kinds of options, but one of the options is low voltage. And it's an auto transformer, so you can change what starting values you want. You can have it start at 65% voltage, 85% voltage. And the reason why they give you those varying values is the lower the voltage, the longer it's going to take to start. So if you can start the motor up at 85%, then what we learn is like, okay, that's going to take less time. But be mindful, you keep adjusting those voltages, the torque that's available to you is directly proportional to the voltage. So if I start the square of the voltage, so if I drop that voltage by 0.65, that's 0.65 squared, right? So now you're talking like 0.3, 0.4. Now you've really got way less torque. So it's possible that whatever mechanical load you have might not be able to spin because the voltage is so small. So that's why they give you some additional options there. We will note, though, too, that it's proportional to the voltage and the resistance, right? The R2 resistance, that's the induced torque. And so what we'll find is you can vary this value of R2, and all it's going to do is change the speed of operation. And only 3 test questions, but like I said, 10 parts or so per each. Because a lot of it is boom, boom, boom. What's the speed? What's the pole? What's this? What's that? And stuff that you should just be able to plug and chug pretty quickly. Excuse me. And that's about it. But give you induction motor with some nameplate data, determine operating parameters, and nameplate usually tells you mechanical speed, right? At full load. You should be able to estimate, we did that in class, right? You should be able to calculate synchronous speed. Maybe calculate efficiency. I tell you operation, that type of stuff, what you should be able to do. Power flow, so losses in the machine. So that arrow where we were dropping out powers, you should be able to calculate that. And then finally, if I tell you an equivalent circuit model or give you the parameters to be able to draw an equivalent circuit, you should be able to find operating parameters. So pull-up torque, starting torque, synchronous speed when starting torque occurs, efficiencies, all those different types of things with these questions. And I've been babbling straight for 30 minutes, so any questions for me? Yes, sir.
For the test, can you go over how the short circuit one looks again?
There is no short circuit test, right?
Yeah, but how the, oh, I can't remember it actually, but what the different circuits look like at the conditions, so when you're.
They look exactly the same.
But didn't you say one of them goes through the rotor and then one of them goes through the other load, I guess?
Here's the machine, right?
Yeah.
The key is based on this, R2 over S. Okay. Under locked rotor conditions, S equals 1. So my circuit can simplify to this. It's still the same circuit, right? It just looks like that because R2 there. Under no load, so this we'll call it locked rotor, under no load, which means S is almost 0. What my circuit becomes now is this, because there's no current going in here because that resistor is essentially an open circuit, right? There's very little current flow there, so we can neglect it. So under those conditions, if I measure the voltage and the current and the power, right, just like we did for transformers to get that angle, you should be able to calculate Z, right, with that. Same thing over here. V, I, and P, I should be able to get Z. The difference over here, this is R1. Come on, stop it. Plus R2 plus JX1 plus X2, right? And over here, all we have is R1 plus JX1 plus XM, right? Because we're just ignoring the R sub C. So it's still the exact same equivalent circuit. It's just that some of those terms go away because our slip is either so high or so low that we have tons of current flowing through or we have no current flowing through our rotor circuit. And then the DC test, everything's shorted out. Under DC conditions, we only have R1. Now that's when you got to look at it and see if it's configured in Y or delta. But all you have is R1. Why? Because this is an inductor over here, right? And what happens to an inductor in DC? Shorts out. So there's no current going into the rotor circuit under DC conditions. Just a short circuit. Does that answer your question or?
Yeah. So, and then so then you use all these to calculate just the parameters of the actual.
The equivalent circuit?
Yeah, so you use these to calculate R1.
Well, you need that, but then you also need, remember, because there's no good way of determining what X1 and X2 are, you
Right.
still need this table to be able to calculate X1 and X2.
So you know the current through the circuit for each condition. Right?
Yeah, you got to measure that, right? It's a test, so you got to measure those parameters.
Yeah.
So you measure
So
B,
that's
I, and P.
You'd be like, in this condition, you get like this much current, and in this condition, you get this much current, and then you can calculate the resistances to the R1, R2. And then you have to use the NEMO design for that table to calculate X1.
Right. Once this one's going to give you X1 plus XM. This one's going to give you X1, X2. So you'd use a table over here. But keep in mind, when you're doing the locked rotor test, that's working the motor really hard. So normally we run this at, let's say we run it at 15 hertz. We run it at a much lower frequency so that we don't pull as much current, because the synchronous speed is really high at that point. So we're pulling in a lot of current. So if this is only operating at 15 hertz, these X values are at 15 hertz as well. Well, because it's 2 pi F times L, right? So if you run that at 60 hertz, you're going to have to multiply those values by 4, because we're looking for the equivalent circuit at 60 hertz and not 15 hertz.
Okay.
So that's where you would need to adjust for the frequency, because you want to run locked rotor at low frequencies. In the lab, we didn't have the ability. We don't have a 15 hertz power supply. So, we're stuck with running it at really high values, and that means we're killing those motors.
So you can calculate your L and then.
You can calculate L, but you don't need to, right? If I know that this is XL at 15 hertz, how would you calculate it at 60 hertz? You multiply by 4, because you're going to divide by the original frequency to get 2 pi L, and then you multiply by 60 to get 2 pi FL, right? So you can go all the way back to L, but if you just do it as a ratio,
Yeah.
it's linear. So that's the easiest way, I think, to do it.
Yeah, so you give all those parameters and calculate R1, R2, all the other values based on those parameters. Okay. That makes sense.
You got it.
Oh, I just had a question on the homework. You said that the torque doubled.
Yeah, because if you remember,
Does that mean that the power doesn't change though, right?
sure it does.
So is that linear portion that you were talking
Yeah.
about?
So if we're over here and we have the speed, right? Because we doubled the torque, we're just assuming it's linear. We got to start someplace, right? So we can't just guess. So let's just say it's linear. So if this is 1 unit, this is a doubling, right? So our slip, let's say this is slip 1. This is 2 times slip 1. So for a halving of the speed, or the, a doubling of the torque, we would double the slip, and now we can calculate a new operating speed. And since power equals torque times omega sub m, the speed has gone down, right, based on the slip, but the torque is doubled. So this is 2 times, but this is a ratio, right? That's that 1 minus S over S thing that we have to worry about. So that's why it's not a direct, it's a doubling of the slip, but it's not a doubling of the speed. Okay, so it's just a way of going back and forth and comparing the two. That's why we say that. And again, we're just saying it's doubling because we got to start someplace. We have to have some approximation to do that.
I had a question on the answers with the calculus for this homework.
Okay.
For problem number 2.
Yeah.
For F, it looks like you divided by 2 into the 2-pole machine, but I think it was 4, which would then impact your.
Oh yeah. That should be 4. Yeah. So this should be
That should be
1800.
18, and then the other 2 would be double that, right? You're dividing by half of 9.
What other two?
The development
Yes,
of-
yep, yeah, so you'd have to divide those by, whatever the speed is. So this is gonna be divided by 2, that's gonna be divided by 2. So they'd be double.
Um, first one,
Problem 1?
yeah.
Yep.
For D, how do you come up with, or I guess I'm seeing it, with this, but why is it not 900 minus 873 for 27 RPM?
For C?
D.
D. No, it should be 27. That's just a typo.
Oh.
It's got to make up the difference in speed. So it's 27 RPM.
Actually, D, well, I had 900.
For E or F?
For E.
Well, so the speed of the rotor field with respect to the stator field. So if it's the stator, the rotor is spinning at synchronous speed.
Okay.
So it spins at 900 RPM. The rotor field with respect to the stator field, they're spinning at exactly the same speed. So that's 0.
So why, that's why we were running the one above for them, 900 for the one above?
Yeah, it's right here.
Okay, he just said 0 if you follow the line. 0, okay.
Yeah, I guess it's the same, it's got the same spot, but one's 900 RPM and one's 0.
Oh, you like copy the work.
Right. Yep. But that again, the important part is like, what's the rotor field spinning with respect to something that's not moving? It's rotating at synchronous speed.
Which makes sense.
Yep. But then the rotor field and the stator field, they're spinning at the same speed, which has to be the case, because if they weren't, you would not get constant torque out, which you have to have. So we rotate them at the same speed. That's the beauty of these things. Because if they didn't run at if they didn't have a constant torque, they would not be out there. They would be gone. Because again, talk to Reed about mechanical systems that don't have constant torque. They vibrate, they rattle, they don't last. If the torque is constantly changing, those pumps are splashing water or whatever process, it's fast, but it does, and it would just destroy any mechanical system. Mechanical systems like nice, consistent. In electrical, it's not so big a deal, right? I can flip open on and off a switch, the lights, turn on and off, no big deal. A mechanical system just go on and off instantly, they don't exist, not that I'm aware of. Maybe Reed knows some, but you have momentum. And we have momentum in electrical stuff too, right? Because an electron does have mass, but it's so minuscule, it's not a big deal to interrupt them. Yeah. The analogy is driving in a car and hitting a brick wall. How are you gonna feel if you get out of the car? Probably not so good, but if you might get out of the car, yeah. But that's the other thing too. You don't actually stop instantaneously in a car. That's what they call crumple zones. And cars used to last a lot longer, so they'd have insurance on them. They would last, they could rebuild them. But now the way that they're designed is they have motor mounts that are explosive. So the engine drops down and then you have this huge crumple zone in your car. So it provides safety. That's why you'll never see in vehicles, even like electric vehicles, why do they have a frunk? They don't need it, right? They could cut it way back, but they need it for crash protection. Crumple zones. You don't need as much in the trunk because you're more likely to get, head-on collision is where you would stop quickly. Where rear, it's less likely. I'm not saying it won't happen, but it's far less likely. Any other questions? Feel good?
How about the very last question?
What's that?
The very last question on number 4.
What about it?
Let's see. Okay, I wasn't quite sure, so I just put down 2 sets of answers for different cases because I wasn't sure if it was you're going to hold the power constant or if you were holding the shaft speed constant.
So you're talking about for part C?
For part D,
No, so because you have a torque versus speed characteristic that looks like this, right? If you double the torque, the speed has to change. So you can't have a constant speed and have a change in torque, which you don't want anyway, because induction motors, that's not how they operate. If you wanted constant speed and variable torque, then you would have a synchronous machine, right? But induction machines don't have constant speed. Doesn't exist. Does that answer your question, Arthur?
kind of.
Okay. How can we expand?
So I get that, it's related to the, P equals, T times omega.
Yeah.
And so, it appears that if you double one, the other one has to have.
Well, it only does that because of this characteristic here. We're assuming that this is the straight line,
Mhm.
whose the slope of that, right? It's going to be equal to 1. So if we double the torque, we have to reduce the slip by a factor of, the same, which is 2. But that's just an assumption because we have to start someplace. So it's the slope of the torque versus speed characteristic. That's why we just take that as, hey, we have no other way. So let's just say it's a slope of 1. Is that any better?
Yeah, I'll kick that one around the old block a little bit. Thank you.
Okay. Yeah, it's just looking at the curve. It's the slope. So it's basically the change in Y over the change in X, or we should say speed, but we'll call it slope because it's analogous to that. And that's going to be equal to our actual, not our slope, our S. And that's the slope that we're talking about here. So we're just going to assume that that slope is 1. So a corresponding change in torque, an increase in 2, means you have to drop the slope by half. If you double the torque, you have to double the slip.
Okay. Which I get that, but I guess what I'm getting at for like C, I guess it appeared to me that if you're asking what happens to the shaft speed of the motor if you double the torque, obviously. So
Yep.
I just thought that, well, if you double the torque, then that's the shaft slows down.
Correct. And that's exactly right. And you can
Okay.
see that with this curve, right? You can see as you increase the torque, you slow down the machine. Yep.
Okay. And then for D, I wasn't quite sure, I guess, what was being asked, I guess is what I was getting to. So it was, you have 2 scenarios, I guess. If you hold the, if you're going to hold the power constant, then
I'm not holding the power constant.
okay. So then if you hold the shaft speed the same and you increase.
No, the shaft speed is not the same either.
Oh, it isn't. Okay.
All we're saying is the torque is
Mhm.
going to go up. This speed is going to go down by a little bit, right? Because the slip is a ratio. So my power is going to go up, but not a doubling. It's
Oh,
going to
okay.
increase, but not by a factor of 2.
Okay.
Yeah, none of those are constant. Okay.
Okay. So yeah, that last one was really the only one that I got hung up on.
Okay. Read.
When you look at that curve right there, your peak power is applied at your pull-out torque now.
This is pull-out torque right here.
Yeah, basically, to get the power, you multiply both of those. Right, so you multiply.
Power equals torque times omega. Yep.
Yeah, so you get your peak power is that.
No, I never said that.
Okay, so. Oh, I guess it's not linear really. Why is that?
Well, because power is torque times omega, right?
Yeah,
So it depends on where that pull-out torque occurs. What if I have this?
oh, okay. So it's just. Right. So what you have to do is you have to multiply those two X and Y values together and then block that, and then you see where you're at.
Exactly.
Okay.
Yep.
For your maximum power.
Yes.
Okay.
Yep.
Where would you pull up for beyond that? Would it be 0?
Yeah.
Then you're not applying power.
Yeah, because it's not spinning. But that, again, go back to our lug nut example, right? You can be jamming on it all day, putting tremendous amount of torque, but there's no power because there's no movement. Which doesn't seem to make sense, but talk to our mechanical engineering friends. They define power, right, as the torque times the speed. If it's not moving, you're not putting any power out. You can be working hard, you can be sweating, which is opposite of what you expect, but yeah, there's no power out.
And then this graph, you'd also be supplying 0 power where the torque crosses, or where the torque is 0, right?
Yeah. In either case, if the torque or the speed is 0, the power is 0. Right? It's just a simple pick which one you want. Either the torque is 0 or omega 0, you're going to get 0. So either one of those variables will force the power to be 0. But we know, right, we can't operate at 0 torque because at that point, somebody's going to have to push us. Because if it's 0 torque, it's going to stop spinning, right? We live in the real world. There's friction and windage losses. It's going to slow down. So the only way we can run it at our torque is 0 is somebody's cranking it along and helping it. So at that point, it's not an induction motor. It's just a hunk of metal that's being rotated. Any other questions? Questions? Nothing else? Going once? Twice? All right, sold. So don't forget, test on Thursday. You have the announcement. Make sure you have your 8.5 by 11. We'll have the test in here for those who want to do it in person. Online, make sure you give yourself enough time to upload. And we'll go from there. Have a great day, everyone.
See.